1 minute, please. Can you see my screen, please?
Yes, we can.
Okay, so my name is Niyi Taiwo, and I'll be taking us through descriptive statistics. I will try to be as down to earth as possible for those of us who might be new to the topic, and I'm hoping to be able to tidy up in reasonable time so that we can have some exercises done with SPSS. So for a start, I would like to just talk about the research process cycle. I always like talking about this because that is like the foundation for everything on research methodology. So we start from the question and it goes down to reporting our findings. And the cycle continues with literature review, the hypothesis, the approach and design, that's your research designs, sample size calculation, the sampling methods, measurements and variables, data collection, and data analysis. And this is what we are talking about. One of them is descriptive statistics. I want to just quickly remind us, I'm sure you will have been introduced to this, the type of data. Because the type of data will also determine the kind of analysis that you will do with your data. We have the quantitative or numeric data, which is further classified into continuous or discrete data. And then we have the qualitative or categorical data, which is otherwise classified to nominal and ordinal data. I believe I'm taking this class with the assumption that we have an idea of what I've just said now, because it's going to be cardinal in understanding what we are talking about. So when we get to the strategies, the analysis part of our research methodologies, there are some analysis strategy. When you are working with one variable, that is univariate variable, you have a particular kind of analysis that you do here, which is basically the descriptive statistics we are talking about. The bivariate and multivariate analysis are the inferential statistics, and that we'll be discussing in a fortnight, at least some basic inferential statistics. So invariably, this is what we are talking about, the univariate analysis. And when we talk of descriptive statistics, there are just two cardinal things we are trying to do. Number one is to organize your data. And number two is to summarize your data. When we are talking about organizing, it's either you have it in tabular form, that's tables, or you have it in graphs, that's organizing. And when we are talking about summarizing, we have like measures of central tendency, measures of dispersion. That's how to summarize your data. And like I said, towards the end of the class, we'll try and do a bit of analysis. I have like a sample data on SPSS that will just see how it is done. Now, for the univariate or one variable data analysis, this is basically a summary of everything in descriptive statistics. I just spoke about the measures of central tendency and measures of variation. These are the two things. In central tendency, we have the mean, the median, the mode. These are things we should be familiar with. And in the measures of dispersion or measures of variation, we have variance, standard deviation, range, percentiles, interquartile range. We also have what we call deciles or deciles. So this one can also come as part of what under variation. And when you have your data, especially if it is quantitative, that is why we have continuous variable here. If it is quantitative, you can check for the distribution. If it is normally distributed, or it's exponential, or it's uniform. Uniform, it's like when you have a constant variable. And then under the same continuous variable, we can have histogram, we can have box plot, stem plot, dot plot, line chart, time series plot. I will show us examples of this chart. Now, when we go to qualitative variable, because you remember I was mentioning it, this one is quantitative. When we go to qualitative variable, that's where you can have frequencies or plots. The type of plot you have here is different from the type that you have under continuous variable. Here you have bar graph, pie chart, and Pareto graph. And I will show some examples of that. So it's under the qualitative variable that you have count. That's where you have frequency table. You have your frequency itself, percentages, and odds. So this is just a summary of what we expect to see in descriptive statistics. So let's just continue. So we use descriptive statistics as researchers to report on populations and samples. The purpose of descriptive statistics is to describe the data that you have. That's where the name came from, to describe the data that you have. So by summarizing the information, descriptive statistics makes you to easily comprehend, the characteristics of a group. And if you had gone through maybe any paper, normally the results section starts with descriptive statistics, talking about the population that you were working on, a summary of their characteristics here and there. And the characteristics is based on either their quantitative variables or their qualitative variables. So depending on what variable you are talking about, there's a particular way to summarize it. On the other hand, inferential statistics allow researchers to make decisions or inferences. That's where the name came from, or inferences by interpreting data pattern. And that is what we'll be talking about in the next class. So descriptive statistics helps you to easily comprehend a group statistics or characteristics rather, while inferential, it's what you infer or project or bring out from the sample statistics to talk about what is observable in the population itself. So we have a population and then you have a sample. If you are able to get the data from a population and you are able to analyze everything, that is what we call parameters. But if it is from the sample that you are able to get your data and then you are able to analyze, that is what we call statistics. So invariably, we use statistics to make inferences on the population. What do I mean? You want to do a study most of the time, and I'm using the word very carefully, most of the time, you cannot access the whole population because of time, cost, logistics, and many other hindering factors. So you take a sample. You take a sample and then you work on that particular sample. And this sample is supposed to be representative of the population. So from this sample now you calculate all that you are trying to calculate. And whatever you calculate there, you are now inferring that this is what you expect to see in the population. This is what you expect to see in the population by virtue of the sample. That is why we call analysis from sample statistics, and the one from population, we call it parameters. That's just a small brief. So we want to describe both the samples and the population. And like I said, the population is just a matter of inference because most of the time we don't have access to the whole population. Look at this example. We have two groups here, class A and class B. And these are their weights, so to say. Just as an example, we have 102 kilograms, 128 kilograms, 131 kilograms for class A, and on till we get to 97. And in class B, we have from 127 to 105 kilograms. Now, each individual may be different. If you try to understand a group by remembering the qualities of each member, it becomes challenging and you fail to understand the group. Now, the question is, which group is heavier? And we have this data of 13 students in class A and class B. I mean, by looking at this, it's challenging to be able to say this is heavier or that is heavier, because you will see some high values here, like 131 here, like 140 here. Likewise, on the other side, I think the highest we have here is 162. So it's difficult for you to actually pinpoint which is heavier. But with the use of descriptive statistics, we can see that they are roughly the same. Both of them have an average weight of 110.5, 110.2. They are roughly the same. And that you can easily pick by the use of descriptive statistics, unlike trying to look at the raw data to pick what is better. So like I said at the beginning of the class, that descriptive statistics is basically to either organize your data or to summarize your data. And for organizing, I said you can use tables or graphs. For summarizing, I remember I said you can use measures of central tendency, measures of variation. So look at like a circle. When we say measures of central tendency, that means everything is tending towards the middle. You are trying to know the unique or the central or the typical kind of value from it. And on the other side, when you say measures of variation, you are trying to look at the spread from the center, how far it goes. So those are the two ways to summarize your data, while the first one is organizing data. Let's start with a small chart to give us a summary. So that's descriptive statistics. You can organize, that is your data in tables or graphs. You can summarize your data in either measures of central tendency or variation. So for the organizing of your data, the tables, we have frequency distributions and we can have relative frequency distribution. For the frequency distribution, we use it for both categorical or ordinal data and for continuous data. Let me just quickly take us back. I said we have data. Data can be quantitative or it can be qualitative. Quantitative can be continuous or discrete, while qualitative can be nominal or ordinal. So because I'm going to be making references to all these terms as we continue. So when we are organizing data, they are good for categorical. Qualitative variables are also called categorical variables, while quantitative are called numerical. They are numbers, numerical variables. Okay, so let's continue. For tables, I said we can use it for categorical or ordinal data and for continuous variables. And that is where in continuous data, and that is where you actually classify them into ranges or groups. So frequency table is a table that displays the frequency of various outcomes in a sample. Each entry in the table contains the frequency or count or tally, with a particular group, or when you have group intervals, and then it organizes the distribution of values in the sample. The objective is just to give you an insight, on the spot insight about the data, that cannot be obtained by looking only at the raw data. And you understand what I'm talking about now. These are examples of about 5 different tables. So let me call this one table A, this one is table B, this one is C, D, and E. So looking at table A, it says number of toy cars sold and the frequency. Just by looking at that table, we can say that in the month of May, that's where they have the highest number of toy cars sold. Because, if we are to add everything here, I'm sure it's more than 100 or close to 150. If you have been looking at the raw data, it will have been difficult. But from the table, you can easily pick it. Likewise, on table B, talking about satisfaction, we can say that only 5 people were very dissatisfied with whatever they were asking about, just because the table had organized it that way. Likewise, in table C also, there are some numbers, the frequency. We can say that number 5, number 7, number 8 had the same frequency, because they all appeared twice. And I'm sure you know about tally. Tally is just another way of organizing your data, where 4 lines means 1, and the line crossing them means 5. And we can see here that number 2 has the highest frequency of 9. Either by looking at the tally or by looking at the frequency, to the highest distribution of 6. So that's one thing about table. If you are to add all these values, they are much, and you might not be able to easily pick it with your eyes, but when you organize it now using a table, it's easy to bring it out. Likewise, when you have grouped frequency distribution, when the numbers, you have classified them, like many of us do when we are taking age of people in our questionnaire, we have already grouped the distribution, maybe 0 to 9, 10 to 11, or 10 to 19, 20 to 21, on and on like that, And from that group, for example, this is A, B, C. Group B now, you can see clearly, that those between the category 60 to 69 are more. Their frequency is higher. And there's nobody in 10 to 19. That's our group frequency. I deliberately put table A to correct something. If you look at the class intervals, you will see that it is wrong. It says 15 to 25, then 25 to 35. You can't have 2 numbers existing in a group interval, because what if there's somebody on number 25? Will you put the person here or you put the person here? So this table A is a mistake, and I brought it out for you to see. You don't put the same number, on both a class interval and another one. And if you compare with this one, you'll see that that mistake is not here, so that you'll be able to clearly put people where they belong or your data where they belong. Nonetheless, this is just another frequency table, but talking about grouped frequency, where you are trying to group your data into manageable numbers. Now, cumulative frequency. Cumulative frequency is another type of table, and all it means is that you are trying to find the cumulative number of your frequency. So this is your frequency table, and the cumulative frequency is just the first frequency plus the second frequency plus the third frequency, which is what you have here, have here. And 12 is actually the total number of observation. That is what we call cumulative frequency. This is for a number, this is for normal frequency table, and this one is for a group frequency table. So this is 2 plus 4, it gives you 6, 6 plus 2 gives you 8, 8 plus 1 gives you 9, and 9 is the total number that we have here. That's just a cumulative frequency in case you come across it. There's really nothing there, but sometimes you have, what's it called? A table that shows you all that. Then we have a relative frequency table. That one is similar to what we saw at the back, in the sense that here, when you calculate the total of your frequency, giving you 16, you want to know the relative frequency occupied by each category. So this is going to be 2 over 16, and it gives you that decimal point. This one to 2 over 16. This is 4 over 16, 2 over 16, 4 over 16, 2 over 16. And that is how you got all these values. And these values can be converted into percentages just by multiplying by 100. And that's how you got all that. So when you hear of relative frequency table, that is what it means. You are just trying to look at what the proportion of each data group of what they occupy in your data collected. The same thing here, 4 over 20, 5 over 20, 5 over 20, 2 over 20, 4 over 20. And then you have all these. Now, these are already in percentages, but that is relative frequency table. In case you come across it, that is how it is derived. So under the same organizing your data, remember I said we can use tables or graphs. So let's go to graphs and look at the types of graphs we have. We have histogram. And for histogram, you use it to display frequency of interval and ratio level data. Interval and ratio level data are continuous data. Continuous data under quantitative data type. Okay? It's like a bar graph, but there is no space in between the graphs. You cannot use it to display more than one variable. Remember, there was a chart I showed us earlier on when I said univariate analysis. Uni means one. The variable of interest is placed on the horizontal axis. It doesn't have to be, it can be on any axis, but it will show, what you are trying to do. And then you have a rectangle drawn above each class interval with its height corresponding to either the frequency, relative frequency, now you know what that is, or the percentage, now you know what that is. So this is an example of a histogram. If you look at them, they are all bars, but there's no space in between them. They are like matted together. And this one is a histogram of weight, and the percentage of people having that particular weight. So this is weight distribution. And this line you are seeing is just a normal curve superimposed on that distribution to see if it simulates a normal distribution. So this is a histogram. This is another example. Now this is 2 different histograms. Remember I said you cannot use it for 2 variables. So this is 2 different histograms, like I brought together to just make it look a bit beautiful. We have the systolic blood pressure, we have the diastolic blood pressure, So this is the histogram for the systolic, this is the distribution for the diastolic. But that's how a histogram looks. There is no space in between those bars. So when you see a histogram, you can't miss it. It is easy to identify. They have bars, no space, cardinal distinction, no space between the bars. That's histogram. This is another example of a histogram, weight of students. So let's assume, those of you listening to me now, I want to take your weight, and then I have the weight in intervals, already classified in intervals in kilogram and the frequency. So that is what you have. And as you can see, there is no space in between the bars. That's why it is a histogram. And this is a symmetric histogram. Sometimes we will see a histogram that is very perfect, where the left side is a mirror image of the right side. So let's imagine that we divide this into two. You can see that the left side, is similar to the right side. That's what we call a symmetric histogram. For example, if you are taking the height and you are plotting this against the weight of people, it's supposed to balance out as symmetric. But sometimes we have what we call left side is longer, by the time you divide it into two, unlike the right side. This one is skewed to the left. You have a longer tail to the left. So when you have a histogram, you should be able to describe the symmetry of the histogram. So we have what we call skew, and then I'm going to introduce another term as we continue. So here it is skewed to the left, while here it is skewed to the right. You can see that here, the right part is examples like that. Maybe you are plotting those that are very expensive, and are more like extended onto the right side of your normal distribution curve. So if we are going to superimpose our normal distribution curve, you can see that it is longer. This aspect is longer, and that is a right skewed histogram. And this one is highly skewed, it's even much longer. The previous one was moderately skewed. This one is even more longer. It has a longer tail. That's how you describe your histogram when you have it being plotted. So skewness, like I've been talking about, left skew, right skew, is a measure of asymmetry of the distribution. The first histogram we saw was symmetrical. So the normal distribution is symmetric, and the skewness is 0. However, if you have a positive skew, you have a long right tail, something like that. A negative skew, long left tail, something like that. All right, so that is for skewness. Long right tail, long left tail. We continue. This is just for the A students. We are not going to go through this, but there is a way you can calculate skewness. When you have to let you know that it can be calculated manually, but normally it is done by your software and it's done in a jiffy. So these are the types of shapes of histogram. This one is the symmetric one that seems to be balanced. This one is skewed to the right. This one is skewed to the left. Okay. And then we have what we call the kurtosis. I'm going to be talking about that as we continue. Kurtosis. So let's just continue. Kurtosis is a measure of the extent to which observations cluster around a central point. So for a normal distribution, the value is also 0. So we can have what we call leptokurtic histogram, where it is peaked, something like this. You can see that it is peaked. And we can have platykurtic, where it's something like that. It's like flat. I will show us as we continue. Platykurtic are flatter and more dispersed along the x-axis. Leptokurtic are more peaked. They are close together. So it has its own formula, which we are not going to go through, but at least for you to know that it can be calculated. And for a normal distribution, the value is 0. So this is peaked. This is the leptokurtic. If you look at it, you can see that it's peaked. Unlike the normal distribution, that it's a bit like a bell. This one is together. The bell part is a bit narrower. That is what we call the leptokurtic. Comparing this with this, you can see that in case you plot a histogram, this is a summary of a variable h in a given data set. All I'm trying to bring out from this is that your data analysis software can bring out the value of your kurtosis and the value of your skewness, just by the click of a button. And we are going to do that as we continue. Okay, so that's a normal distribution. and it looks like a bell. You will have been hearing about the bell-shaped, you know, that's what it means, bell-shaped design. That's a normal distribution. All right, so let's look at another graph. The first one we have looked at is the histogram. And then the next one is the bar chart. And the bar chart is used to display nominal and ordinal data. These two are examples of qualitative data, nominal or ordinal data. Here, you can have spaces between the bars, unlike in the histogram. And one bar chart can present two or more presentations, and you will see, I'll show some examples. The bars are separated, you know, to emphasize the fact that they are separate categories. Remember, qualitative data are also called categorical data, you know. So that's why there's a space to show that there are different categories, and the height of each bar is proportional to the frequency or percentage of that category. This is an example. Now it's looking at home and international students in a particular school, you know, and then we have those that are British home students, those that are international students by color coding. So in 210, the British home students are more or less like maybe 40, let me say 39 or thereabout, while the international students are 20. That is 210 for men, you know, and then they did for women also. So you can see the way it has organized. The way it has organized the data. It would have been difficult to look at all this data in your raw data sets to be able to really bring them out like this. But it has organized it so that by year, you can even pick it out. And even looking at these charts, we can see that home students, the British home students, are more all through the years. It's as simple as that. You can just pick it that they are more all through the years. And then in the year 2011, the men, they are like closely, you know, matched. They are like closely matched. But for all the other years, the home students have higher frequency or higher percentage, depending on whatever they are using here, you know, compared to the international student. That's what a bar chart does. You know, this is another example of a bar chart. There are different designs. This is another example of a bar chart. From here, we can say the yellow color is more frequent. You know, maybe children's favorite color, we can say yellow is the best, is the most favorite color. You know, while green is another example. You know, looking at rating, we can say number 5 has the highest rating by virtue of it is the longest. Don't forget the space in between the bars, which is the cardinal distinguishing feature between a bar chart and a histogram. Please don't forget that. It's as simple as that. Now we have what we call a Pareto diagram. A Pareto diagram is actually a combination of a bar chart with a cumulative frequency. The cumulative frequency that I told us how it was calculated earlier on. You know, so that is the Pareto diagram. So you have your bar chart because you can see that there are spaces in between, and the cumulative frequency is superimposed, you know, on top of the bar chart. That's a Pareto diagram. There are some kind of data that you can use to bring it out. It makes it look a bit appealing, makes it look a bit scientific. So there's really nothing there. It's just a cumulative frequency chart superimposed on top of a bar chart. As simple as that. Then we go to a pie chart. All of us know what a pie chart is. We've been doing it even from second center, and then you do all manners of graphs, you know, to divide it into sectors. Now, the good thing is that a pie chart and a bar chart are used for the same type of data, categorical data. That is why it's still nominal and ordinal data. So it displays the categories, but this time around, it is like in a cycle with different segments. The segments can be shaded differently or patterned differently or colored differently to signify the particular category you are talking about. It's usually used to describe a single distribution, but one can use 2 or more pies to compare distribution. You first draw your circle, use your relative frequencies to subdivide the circle into corresponding sectors. Normally, we divide it by 360, which is the degree of a circle, you know, and then you get your proportion for each of the segments. This is an example. Looking at this pie chart, we can say without going further that Germany has the highest proportion, and the least is Australia. That is how fast it can give you an answer. Remember, we are talking about organizing your data. These are two other examples. Population of countries of the European Union in 1998 and 2007 by percentage. And then if you look at, let me say this is A, 1998, and this is B. And we have the color coded here, for all the countries. We can see, although they have put the percentages on top, but you can see that you can compare 1998 with 2007. For example, looking at, let me say Poland. Poland in 1998 was 8.0. Poland in 2007 was 7.70. So there's a slight decrease. As there's a slight decrease in Poland, there's a slight increase in all other countries, because here we have 29.7.4, here 0.7. So that's a pie chart. They are all color coded to signify that they are different categories. And this is another example, telling you that you can even have a descriptive statistics where you have both, the bar chart and the pie chart representing the same data set, because the pie chart and the bar chart are for nominal and ordinal data. Your pie chart can also be further designed to look like a donut. It's still the same thing. There's an imaginary center somewhere here, such that all these lines can be extended to give you, the rate. However, the percentages are there. For example, Russia has the highest value, and then the least is Australia. That's countries by area. It is also an example of a pie chart. And then I have an example here too. So I'm based here in Jos, and JUT is the Jos University Teaching Hospital, and we have the general outpatient department where people just go for their health care. So patients visiting JUT were asked to rate the quality of their experience as either being excellent, above average, average, below average, or poor. And as you can see, by virtue of this category, it is a qualitative data. And this particular type of qualitative data is what we call the ordinal type, because it is going either in an ascending order or descending order, starting from being poor to below average, average, then above average, and excellent. And then we have the response from 20 patients. Imagine having it from like 50 or 100 patients. It's difficult to quickly know which one is the best or which one is the worst. That is why we need to organize it. So that's what we are talking about. Now, we have done a table here. And from the table, unlike when it was here, it will be difficult to really know their frequency. So from this table now, we can see that excellent is just 1 out of the 20. Poor is 2. And the highest one is above average, which is 9/20. That's a table for frequency distribution. Then we can go to relative frequency, and let me go back. So if we are to do relative frequency now, so our RF, relative frequency, will be 2/20, 3/20, 5/20, 9/20, 1/20. Whatever figure you have here is your relative frequency, which is what we have here. I discussed earlier on how we arrive at relative frequency. All right, so, and the percentage frequency is just multiplying our relative frequency by 100. So we have 10, 15, 25, 45, and 5%. That is how we arrived at that. Now, this is an example of a bar chart for the simple reason that they are in categories. And like I kept emphasizing, you can see that there are spaces in between them. And we can see clearly from our bar chart that above average has the highest score of 9. And excellence has the lowest score of 1. You get the point. That's the bar chart. And like I said, it's a qualitative data. So the same way we have a bar chart, we can also have a pie chart to represent what we are talking about. And you can see there, that above average is 45%, excellent is 5%, and then average is like a quarter of the whole response. That's about 5/20. So that's a pie chart. The previous one is a bar chart. As simple as that for descriptive statistics. So the stem and leaf plot is kind of table, where each or digits and a leaf, usually the last digit. So here, okay, so this is the stem where you have 1 and 2 as the stem, and these green ones are the leaf. So invariably, this one from here to here is the number 120 to number 129, where 1 and 2 is the stem, and then we have the extensions there showing the distribution of the numbers. Now look at this particular one here, A. We have number 15, 16, 21, 23, 23, 26, 26, 30, 32, and 41. And you can look at the stem. The stem are the first numbers, and we have it from 1 to 4. Where this particular number here is number 41, because we attach it to this number. This particular number here is number 16. This one here is number 15, which is representing these two numbers. This is 23, 23, 26, 26, because this is the stem of the distribution. So this is the distribution, but you just look at this, it gives you a kind of organized way for you to know how it looks like. So I can actually say for this chart on A that those under 20 are more, because I have 5 of them, 21, 23, 23, 26, 26, and the numbers under 40 is only 1, and that's number 41. And how do you make a stem and leaf? You arrange the data in order, either ascending or descending. Separate data according to the first digit, then make a display by using the leading digit as the stem and the trailing digit as a leaf. Look at this example also. This is the stem, this is the leaf. From this particular chart A, stem and leaf, I can say that I have number 35 and number 41 as the two commonest number. This is 35, 35, 41, 41. This is number 50. This is number 53, 56, 58. And I can say that those numbers under 40 are the commonest, because I have 5 of them there. So I have number 10 here, 13 here, 16 here, And looking at this particular chart here, I can conveniently tell you, without bringing out all the numbers, that my mode from this stem and leaf is number 17, because it's the one appearing 3 times. It's as simple as that. My mode is number 17. I have 17 appearing 3 times, out of all the numbers. So that is one way. And I have number 50 twice, 50, 50 twice, So that is stem and leaf. I think there's a small class example here that I will quickly do with us. So like I said, when you are doing stem and leaf, arrange your numbers in ascending order. Topwell got his friends to do a long jump, and these are the results. 2.3, 2.5, down to 5.0. Say construct the stem and leaf. So like we said, you start from the first digit. So I have 2 points, then I have 3 points again, I have 4 points, and then I have 5 points. So I have 3, I have 5, I have 5, I have 7, I have 8. These are the numbers I'm picking. And then I go to number 3, I have 2, I have 6, I go to number 4, I have 5, I go to number 5, I have 0. So that's stem and leaf, as simple as that, sharp. There's no long story. And from this stem and leaf, it is clear that the number under 2 points are the commonest, and only one is 5.0, another one 4.5. It's as simple as that. But it helps you to organize your data such that looking at it at once, you can be able to pick out what it is. Frequency polygon is just a graphical device for understanding the shapes of distribution. They are just like for histogram, but they are good for looking for comparing of data sets. They are also good choice for displaying your frequency and cumulative frequency. So if you look at this data, this graph rather is a histogram, because there's no space in between. How do we get a frequency polygon? It's just by having a point at the middle of your bars and connecting it with a line. Look at here. This is the middle, this is the middle, this is the middle, and then you are just connecting it with a line. That line is the frequency polygon. This black line here is the frequency polygon. It helps you to look at the shape of your data. See, it's clearer here. That blue line is the frequency polygon, where all this red dot is the middle of your bars in your histogram. So connecting them is your frequency polygon, and that is a frequency polygon. So this is with the bars removed. I can give you a shape, of your distribution. Likewise, this one too. It is a frequency polygon with the bars removed. Remember, it's starting from, the beginning and ending with the last one. So when you see something like this, it's a frequency polygon. And this is two frequency polygons to compare a large target and a small target. Dot plots is another type to graphically summarize, to organize your data. They can be used for categorical or quantitative variables. They take the form of a bar graph or histogram. So you can see we are having a kind of graph that can mimic a bar graph or histogram depending on the type. So we have two types, the Cleveland and Wilkinson dot plots. The Cleveland is similar to a bar graph, while the Wilkinson is more like a histogram. And I have an example here. This is the Cleveland. You can see it's arranged or stacked in order. It says the books read last summer. So maybe we are looking at the number of children and the books read. So 4 of them did not read any book. 5, this is 6. 6 of them read 1 book. 3 read 2. 3 only 1 person read 3 books. 2 people read 4 books. 1 person read 5. Nobody read 6 books. 1 read 7. 1 read 8. 1 read 9. That is the Cleveland type of dot plot. Where the Wilkinson, you can see that they are just dots, dot, dot, dot. And from here we can say that in the long jump, United States has the highest, distance of 9 points, whatever meter or whatever we are using, while Indonesia has the lowest, of maybe 7.9 or 7.8 thereabout. So this is Wilkinson. It's another method for you to summarize and organize your data. So this is another example of Cleveland. And this is another example of Wilkinson. It's just for you to know that they are all descriptive statistics. Line chart, or graph, also known is a type of chart that displays information as a series of data points, connected by straight lines or segments. So you can see this. There's a data point here, another one here, 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 here. So let me go back. So it's like this can also be a line chart if we connect it. Let me see which one is which, maybe something like that. So that can also be a line chart if it is connected. So that's a line chart for you. And these are examples. And you can compare like 2 different variables to see which one is making a difference, when you are comparing the 2. This is another example of a line chart, for frequency of students, the part-time students and the full-time students. You can see that the part-time students are less than the full-time students by comparing the 2 line charts. This is a time series plot. This one has to do with successive points, time interval. It's like possibly you are, I think some people, this Forex, I've seen this chart in Forex, all these people that are doing Forex sales, normally you have it looking like this. That is a time series plot, a plot. By every time you are checking to see, a change in the difference in a particular variable. So it goes up and down, on and off like that. It's like this ECG, for this heart, when you are taking the heart breathing, that's a time statistics. So as a summary, we have spoken about organizing data, tables, and central tendency, and I'm going to be a bit fast here so that we can. Data is usually computed with interval or ratio data, quantitative data, because they are the ones who can add. We are going to look at mean. We all know what mean is, adding all the numbers and dividing by the total number. That one, I'm not going to spend much time there. So we have class A, we have class B. What is the mean? We have done that earlier at the beginning. Those are the mean. You add all the 13 number and 13 figures and divide by 13. So mean is very important for inferential statistics, but it's not resistant to what we call outliers. You understand? Outlier is somebody or a thing that is far detached from the main body of the system. A person or thing differing from all other members of a particular group or set. So let's assume all of us here in this group, in this class, let's assume we are workers and we are earning salary. Possibly our salary might range from, let's say, 150, maybe to like 500,000 per month. We can find our average. But the moment you bring somebody like Dangote here, it has scattered our work, because it will now move our mean to somewhere to the front, and that is not the truth. So mean is not resistant to outliers. Outliers tends to affect your, or the central measure of central tendency. Like I said, it can make your a bad example of ours. So the example I just gave earlier on, if we are to put Dangote as part of this group, it will make our mean to be extended beyond the normal place it should be. That's just an example of a mean. So when you have a distribution where your mean, when you have an outlier that can cause your mean to be a representative of something wrong, you use a median instead of a mean. You use a median. So is the best measure of central location, that's average. All the data are used. It's affected by extreme values. It's best for normally distributed data, not usually equal to one of the original values. By the time you calculate it, it's not usually one of the original values. It's good, it has good statistical property, and they are usually represented or presented as, you might have seen, mean plus or minus standard deviation. That is how it is usually presented. Median is the middle value when they are ranked in order. That one we all know. When you list the data in order, the median is the point at which 50% of the cases are above and 50% below it. Another name for median is 58th percentile. So we have 13 students, like in class A. If you arrange them from beginning to ascending or descending order, the middle number is the median. It's as simple as that. But when you remove like the first number, you now have 12 numbers. So the 6th and the 6th from up and down divided by 2 will now be your median. I'm sure we all know all these ones, but this one is unaffected by outliers. So let's assume that I have these 12 numbers, and then the 13th number here is 5 million. It doesn't affect my median. My median will still be, the number. That is the difference between median and mean. It's not affected by outliers, okay? If the recorded values for a variable form a symmetric distribution, the median and mean are identical if it is symmetrical. But if there is a skew, the mean goes towards the area of the skew. Like if Dangote was here, our mean will go towards the area of the skew, unlike the median. The median is not affected by outlier. So that is the mode, the median, and the mean, like I said earlier on. So the mean does not use all the data. It is not sensitive or is not affected by outliers, and it has good descriptive measure, but poor statistical property. So when you have a data that is skewed either to the left or to the right, it is better you use your median as your measure of central tendency rather than to use the mode and the mean. That's why I'm bringing up all this. Use your median rather than to use the mean. The mode is the commonest data point in this data here. From here down, we can see that 109 is appearing 3 times, and that is the mode. It's as easy as that. You have your data point. It's possible that you don't have a mode. Look at this data point. There's no number appearing twice. But here we have a mode. Number 3 is appearing 3 times. Okay, and we can also have what we call a bimodal, where 2 sets of numbers can have the highest frequency, number 2 and 5. So it gives you the most likely experience. Rather, in symmetric distribution, they are all the same. Here, if the distribution is symmetric, the mean is the same thing as the median, is the same as the mode. In the skew data, the median and the mode lie towards the skew than the mode. The mode is not affected. Mode is mode. It remains where it is. So if you have a normal distribution where everything is a mirror image of left and right, the mean is equals to median, is equals to mode. And that is what you have here, if it's a normal distribution. So having discussed central tendency, let's look at variation. A range is the difference between the highest number and the lowest number. So in class A here, the highest score is 140, the lowest score is 89. Our range is 51, 140 minus 89. Likewise, in class B, our highest score is 162, lowest score is 80. Our range is 82, 162 minus 80. It's as simple as that. Interquartile range is the value that marks one of the divisions that breaks a series of values into 4 parts. Interquartile, quartile means 4. So our data is divided into 4 groups, 4 equal groups, 1, 2, 3, 4. This one, Q1, is the 25 percentile. That is the one that divides the first 1 quarter from the remaining 3 quarters. Q2 divides the first 50 from the second 50. Q3 divides the first 75 from the last 25. Just like that. It can also be calculated using, what's it called? Softwares. So if we have, like this 12 patients now, for you to find the 3 quarters, you have to arrange them in ascending order. So let me pick it. I think this is 8. This is 9. I think I have 10. I have 11. I have 12, 8, 9, 10, 11, 12. Then I have 14, 14, 14. 1, 2, 3, another 14. That is 1, 2, 1, 2, 14, 4, okay. Oh, my 8 is 2. I can see another 8 here. And then I have 16, and then I have 19. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the first thing to do, if you are to find the quarter, the 3 quarters here, is to divide it into 2. So I have 1, 2, 3, 4, 5, 6. I have another 6 here coming from behind. So 12 plus 14 divided by 2 will give me my Q2. That is 13. So Q2 is 13. That is the median of this set of numbers. Q1 is to count from here and look at the middle. Q1 is going to be 9 plus 10 divided by 2. That's 9.5. That's Q1. And my Q3 is going to be median also here. 14 plus 14 divided by 2. Q3 is 14. So Q1 is 9. Q2 is 13. Q3 is 14. As simple as that. It now says find semi-interquartile range. That's just Q3 minus Q1. That is 14 minus 9.5. And that is going to give us, I think, 5. I think 4.5. Our interquartile range is 4.5. But that's just a class example. It's a very straightforward stuff. It doesn't require any big stuff. So for example here, look at this chart here. We are told to look for the interquartile range. This is the lower quartile, which is Q1. Median is Q2. Upper quartile is Q3. Our interquartile range is Q3 minus Q1. And that is 15 minus 4. That is 15 minus 4. Our interquartile range is 11. It's a very straightforward stuff. Variance is a measure of spread of values. If you look at this one now, it's a bit flat. That's platychotic. You remember our graph and histogram, you know, and this one is leptochotic. So it's a measure of dispersion. That's variance. Look at this set of numbers, 5, 5, 5, 5. You know, if you find the mean of all these numbers, their mean is 5. But this one is a constant. It's not changing, you know. So, but this particular one, we have a higher variance if you are to calculate variance. This one will have a low variance because they are close together. That's how you consider variance. Look at variance here. Variance is you minusing the mean of the number from the class value. So this is the mean of this class A. And we are trying to look at the deviation of number 115 from the mean. We are going to check the deviation of number 102 from the mean. You know, by the time you do that, you will get both positive and negative. This one is less than the mean, so you have negative number. This one is greater than the mean, so you have a positive number. So that's what I'm talking about. And then if you are going to find the deviation of all the numbers, you know, and you add them, you will have 0. You will get 0 every time because the positive number will eliminate the negative number. So what we do is that we find the deviation and we square them. That is the number minus the mean and square them. I'm sure we have done variance before. For example, for 102, if you subtract the mean, you get minus 8.54. When you square it, you have that. For number 105, minus the mean, when you square it, we have that. And if you do it for all the numbers, we have what we call sum of squares. So if we do it for all these numbers, you have sum of square 2,825.39. And in the variance, the last step is to find the average of the sum of squares. And that's the formula for variance. The sum of all those deviations squared divided by n minus 1. You use n minus 1 because most of the time you are using sample. But if you have the whole sample, you don't have to do minus 1. You just put n. Okay, so once you do that, our class number was 13, n minus 1 is 12, and then we have 235.45 as our variance. But it is not helpful because that value is still in squared, and it makes it difficult to interpret. So the next thing we do is to find the square root of our variance, and the square root of our variance is what we call the standard deviation, which you must have been hearing every now and then. Standard deviation. And it reveals the average deviation of the observations. So S squared is variance. The square root of S squared, which is S, is standard deviation. And that's what we have here. And once you have that, you have a figure. For example, now we have 15.34 as our standard deviation. Okay, let's continue. So the larger your standard deviation, the greater the amount of variation from the mean. So when you have, look at this standard deviation, is 3. Look at the way the graph is looking. Look at the standard deviation, is 6. You can see that the graph is flatter. One way to identify how big or how dispersed or how varied a data is by looking at the standard deviation. There's a particular chart I'm going to show you to explain what I'm trying to talk about. So here, this one, there's no standard deviation. This one is a constant. Here, the standard deviation can be like 1, this one may be like 1, this one can be like 3, to see that they are all different one from another. This is what I'm talking about. Look at these two classes. There's a class A and there's a class B. And this is the score for class A. Both of them have a mean of 80. Class A has a mean of 80, class B has a mean of 80. However, when the standard deviation was done, you know, class A has a standard deviation of 5.0, class B has a standard deviation of 15.8. So this one will be written as 80 plus or minus 5. This one is 80 plus or minus 15.8. So this standard deviation has a meaning. It just shows that in class A, most of their scores are close together. Whereas in class B, although they have the same mean, some people are scoring lower, some people are scoring higher. That is what standard deviation tells you whenever you see it already reported. It just shows you how close together the data points are, or how far away they are. That is all about standard deviation. Okay, so it says there is more. I don't know if we have time for that more. For otherwise, I just go to, okay, let me the graphical way to show most of it and show you the upper and lower quartiles, the mean, how a box plot looks like. Many of you will have seen side. That is what we call outliers. Outliers. This is another example of a box plot, and we are going to see how we can chart some, using SPSS. All these are box plots. So that black line you see in the middle of the box plot, that is the median. The lower part here is the lower quartile, Q1, this is Q2, this is Q3. This is the maximum, this is the minimum. And whenever you see any number outside, it's an outlier. Okay, no, let's just continue. So I just want to quickly use the next 5 minutes. Our time is up, it's already 1 hour, to use the next 5 minutes to take us through some samples or example in, what's it called? In SPSS. So while I'm trying to share the SPSS slide, if there's any question, I wouldn't mind to take it. Let me just.
All right,
yes,
thank
so
you
the way.
very much, sir.
All right.
Okay, so while the SPSS comes up, anybody ask question by show of raise of hand? Okay, seems there are no questions.
Are we sure we are understanding all this in English? I hope I'm not.
So we do. It has been so simplified that it's easy for everybody to grasp.
Beautiful, beautiful. Okay, so this is a sample data of a group of people. Can you see the SPSS screen, please, before I continue?
Yes, we can. We can see.
Okay, awesome. So it's a data of like 180 people, 180. You know, I have here an ID number, which does not really make any sense. It's just an ID number. But I have here their age, their gender, their basic metabolic index. This is supposed to be serum cholesterol. It can be anything. This is presence or absence of stroke, which is an example of qualitative data. They are being followed up for a period of time. Do you have hypertension, yes or no? The educational level. Okay, so this is the variable view. You know, at the ID, the age, the sex, the BMI, that's the serum cholesterol, like I said earlier on, the presence or absence of stroke, the time they are followed, had hypertension, yes or no, educational level, and the educational level is non-primary, secondary, and tertiary, like we will see here. So let me first start by showing us how we can do, what's it called? How we can do descriptive statistics. So let me start with age. I can right click on age. You can see here, you know, there's a place that says descriptive statistics. If I click on that, it is going to run the descriptive statistics for age for me. So let me just click descriptive statistics. It's going to show me an output, what's it called? An output chart, which I think I have to share. Are you seeing the output chart, or I have to share it?
Well, I'm not going to see it until you share it. Yeah, that's the issue with it.
Okay. Okay. So this is the output chart loading. You can see the baseline age. So this is an example of a table. It has already like summarized the table. And from here, I can say that age 40, you know, seems to have the highest frequency of 16. If I'm to scroll up and down, that's age 40. And then this one is the descriptive statistics, the one on top here. You can see on the spot, the mean is there, 45.5. The median is there. The standard deviation is there. The range, which is just this difference between the maximum and the minimum, 63 minus 32, is there. So that's descriptive statistics just in a nutshell for age. Let me go back to the data, and then I'm going to share the screen again so that you can see what I want to do. Unfortunately, I have to do a bit of sharing and unsharing so that we can flow together. Can you still see my?
Yes, we can see the. You can see the data view.
Okay, beautiful. So another way to check for our descriptive statistics is to go to analyze. And in analyze, you can see me going to descriptive statistics. And I can come here and say descriptives. Here, I might want to check for maybe many variables and look for their descriptive statistics at once. So I can pick sex. I want to know how many are male, how many are female. I can pick the baseline BMI. I can pick the serum cholesterol. I can pick even the age that we have worked on. I can pick if they had stroke or no stroke, if there was hypertension or not, educational level. I just want to check for their descriptives. And once I run I just say okay, and then I'm going to go back and share the output window for us to see what I have there. So it's loading, beautiful. Now you can see here, this is a summary of all the descriptive statistics of all those variables. This is the total number of the data set. This one is showing 1 and 2 because ideally it's a categorical variable. I shouldn't be running the mean or median. You understand? But for the baseline BMI, you can see the minimum, you can see the maximum, you can see the mean, you can see the standard deviation. So all I'm trying to say is that this has brought out all the descriptive statistics that we need. So presence or absence of stroke, educational level, they shouldn't be done using descriptive statistics. They are supposed to be done using tables, bar charts, and pie charts because they are nominal data or ordinal data. And I'm going to be doing that right away. So let me just go and run a chart for those data. Let me run a chart for those data, and then we can see how that is done. So I will go to graph. For this particular, I will go to graph, and then I will go to legacy dialogues. Legacy dialogues, and I want to run a bar chart, which I said is the same thing as a pie chart. And we can only do that for categorical variables. So let me go to bar chart, and then I'm doing a simple one, and then I will define it. So for the bar, what's it called? For the bar chart, I want to run a bar chart for sets, and then let me just do that first, and we'll look at how it goes. Okay.
Hello, sir, we lost your audio.
Oh, sorry. I'm even trying to, I think I mixed up something.
Okay.
Bar, chart builder, legacy, bar, define. One minute, please. The graph.
Yes, we can see the graph, sir.
Yeah, so that's an example of a bar graph because it has space in between. So we can see the count for men is about 80. The count for women is just a bit about 100. Remember, the total is 180. And then I've just done another graph for those who had stroke or those who did not have stroke. So we can see the count for those who didn't have stroke to be like 100 and maybe 18 here or there. And this one is like 160 thereabout. So that's bar chart. I wouldn't go into how to format the graphs. This is just the basic. I want us to do a histogram, and then we're going to do a box plot. So I will go back to the data set, and then I will pick the particular variables that we can do histogram for. And if you remember, I said histogram can be done for continuous variable. So I can do histogram for age, I can do histogram for the BMI, I can do histogram for serum cholesterol. So let me go to graphs. I go to my legacy dialog, and then I look for where is histogram. Histogram is the last one here. Remember I said histogram is the one that does not have space in between. So let me pick age and put here, and then run my histogram. And then I will take us back to the output for us to see the histogram. So we can see the histogram here. And the good thing with the histogram here is also giving me the mean value, the standard deviation, and the total number of people that is here. For this same histogram, I think, let me see if I can put something on top. 1 minute. Graphs, histogram. I want to display the normal curve on it. And then you can see that's the normal curve displayed on top of the histogram. That's for the baseline age. And I'm just going to quickly run the same analysis, using the same histogram, but this time around, I want to change the variable to baseline BMI. Are you seeing now? Now, I want to compare this particular one for the BMI with that one for the baseline age. You see that the one for the age is a bit flatter, not so pronounced, compared to the one for the baseline BMI. This one looks a bit close together. So when we are talking about platycortic and leptocortic, that's what we are talking about. This one is a bit flatter, this one a bit close together. That is our histogram. And histogram is used for continuous variables, or quantitative variables. The next thing I want to do is maybe to run a box plot. I don't think I need to go through a pie chart. That one is straightforward. Let me just run through a box plot, and then we can close for the day. I've taken much of our time. So I go to graphs. Sorry, let me show us how I'm doing that so that I can share. It's loading. Okay, so I go to graphs, I go to my legacy dialog box, and then I go to box plot. I pick box plot. I want to do a simple one. I want to define it. So what is the variable that I want to check for? Maybe let me look at the baseline BMI as my variable. And I want to check it based on educational level. I put that here, and then I run that. So let me stop share so that we can see the output. Can you see the box plot here now?
Yes, you can see it.
Yeah, and the good thing here is that, what, I can even change the colors, of individual boxes. Like, for example, this one is, what's it called? This one is tertiary. I can put the color of tertiary to like purple, apply. I can come to the color of secondary, maybe I put it like yellow, just to like distinguish all of them. Can come to the color of primary, maybe I give it like a light lilac, apply. I can come to the, I can leave this one the way it is, and I can
Hello, sir.
sincere apologies for the mix up. I've been having a lot of calls coming in. I'm trying to stop them, and it's affecting my connectivity. But I think I will just show us the box plot with maybe 2 more variables, and then we can close. I'm so sorry, but can we see this particular one with educational level, please?
Yes, we can.
Yes, we can see.
And the outliers,
yeah, so
yes.
I will just, what's it called? I will just run the same box plot with 2 more variables just for us to have an idea of different appearance. So box plot now, the simple type, define. So I'll be using, instead of the baseline BMI, I'll be using the serum cholesterol, and then I will just still run it for, okay, so can we see this one now? This is for the serum cholesterol, and I'm still using educational level. You know, so we have some outliers here, we have some outliers here. This particular one here with an asterisk is what we call a far outlier. It's very far from the normal range that we expect, you know, for the others. I'm going to quickly run another one. Maybe I will use for the box plot. Let me just use the gender instead of what's it called? Instead of the educational level, I will use the gender and possibly pick another variable. So I'm going to use okay, so I have another one here. This is the baseline, the age, you know, a box plot of the age with the gender. And as you can see here, there's no outlier. That means that the age was within the normal distribution range. And the way I did it earlier on, it can also be edited such that, you know, you have color coding for different group. I can say maybe for the women, let me put it blue, and then for the men, I can make it maybe green. You know, I can apply, and then I can close my box, and we have something like that. You know, so that's it. It's a very simple way for descriptive statistics. I want to sincerely appreciate your time and audience. By God's grace, when next we are meeting, we'll be talking about inferential statistics, things like t-test, correlation, ANOVA, regression. And I think for the next class, I will try to be more succinct with my time. You know, just hoping that I don't overload you too much, but I'm sure no matter how it has been, you will have learned 1 or 2 things. And I'll be sharing my slides, you know, as a lesson note so that Dr. Lawal will be able to get it across to all of you. Once again, thank you for your time. If there's any question, I have like a minute or 2 to quickly address our questions. But nonetheless, I'm sure we've had a wonderful time. Over to you, Dr. Lawal.
You've had an amazing time. I've learned more than 1 or 2. We've learned a lot. I always learn whenever I'm in your class, and it's a great one. So quickly, let's take questions if there are any. Okay. Any other question, please? We need to know the number, then we round it up quickly. All right. So Grace, go ahead. I think she's the only one with a question.
Good
Grace,
morning,
please go
sir.
ahead.
Yeah, good
Thank
morning.
you for your session, sir. Sir, please, I just wanted to clarify, a scatter diagram, is it the same as the dot plot you're talking about? And what are the differences between this?
Beautiful. So a scattergram is what we also call a scatter plot. It's used for basically quantitative variable, and is the first step you do when you want to do a correlation. So there are 2 different things. The dot plot is a descriptive statistics, and it's not the same thing as a correlation. The scattergram is a type of inferential analysis. That's why I didn't mention it in this class. You know, when we talk about that next class, you understand. So a scattergram is the first step to check for correlation when you want to do a correlational analysis of 2 variables. So, and a scattergram can only be used for 2 continuous variables, unlike in the dot plots, where you can have it for either a continuous variable or a categorical variable. So it is your research question that will determine the kind of graph that you bring out, and the kind of data will also determine the particular type that you use. So in a nutshell, a scattergram is used for correlational analysis and it's inferential.
All right, thank you very much, sir.
Thank you very much, sir. And with that, I think we can give him a round of virtual claps for this beautiful lecture. Thank you very much, sir.
Thank you, Doc.
Okay.
Prof, thank you so much for inviting me, man. God bless you.
Prof.
I'm sure Prof wants to say one or two things. Yeah.
Yes, Prof, it's not true. It's we that we will thank you that you found time. I was just telling them you're busy, that you're known for this internationally, and not just the fact that you teach statistics, but you teach it in a simplified form. You make it very basic. I've been in this class and I'm learning again. But I hope everybody that is here can also apply to what we've been talking about, results presentation, the depth of what people look for when they write manuscripts. It's not just writing manuscripts, but telling the truth with your statistics. And there are things you would see. You think people don't understand these things and you mago. You don't, they see it. They see it because your data tells you what it should be. So you can't have a skewed data. The details will show, and then you'll be using statistical tools that are for a normal distribution, like I noted. It's been brilliant going back to the basics. And even me myself, staying here, learns a lot of new things again.
Thank you so
Thank
much.
you so much. It was so grateful.
Yes.
Thanks for going to be here again in the next session. On that note,